Hello everyone and welcome to this quick tip video. My name is Arvind Krishnan and I work at GoEngineer as a simulation specialist. In this video, we're going to look at a new feature in 2016 in Flow Simulation called Equidistant meshing. This feature is used to get a uniform transition of a local mesh from a small local size to whatever the global size is. So in this study, we see a cylinder and the computational domain around it. It's an external analysis, and our global mesh has been defined as a general setting 3. The equidistant meshing option comes under a local mesh, and the main reason it's local is because the smaller mesh size is for a given region around a particular entity as compared to the entire global size. In this case, the region of importance is defined as the face of the cylinder. We are refining the fluid cell and the partial cells. And here is where the feature, which is new to 2016, is there, which is equidistant refinement. We've used 2 levels, which means it's going to take 2 steps to go from a fine local mesh size and gradually change to the global size. The first step is going to be 0.01 meters radially outward from the face selected, and the second step is going to be a small step away from that, and hence you see that second step slightly bigger than the first one. If you look at what the mesh looks like after these mesh settings, you can see that the global size, as seen on the outsides, is relatively coarse. We had 0.01 meters radially outward as the first equidistant size away from this face, and then the second step, which is slightly more coarse as compared to the first one but finer than the global size. To give further clarification on the 2 steps, we have a second study defined where the first really fine step is small, and then the second coarser step has a bigger distance to cover. And if you look at this mesh, you can see that that fine size is very close to the initial face, and then it very quickly jumps on to the relatively coarser size. And then finally it goes to the global size. In terms of when and where to use this, it's important to note that if you have fluid around a car that you're trying to simulate, where there is more changes in important parameters like pressure and velocity after the car itself, where there's more turbulence as compared to before, you would notice that having a dense mesh before your fluid hits the part itself is not useful in giving you better results. It just increases the amount of computation because all the changes are happening behind the object as compared to in front of it. Similarly, if you're trying to simulate free convection, where there is more movement of the fluid above a part due to buoyancy effects as compared to below it, having a uniform mesh around a part is counterintuitive. As compared to that, if you have a forced convection, maybe where you have a part and you're looking at the temperature distribution around it, then this might be a useful feature to have. Once again, this is Arvind Krishnan, and I hope you find this quick tip video helpful. Thank you.